Okay, so this is the notes from Chapter 2, Section 4, where we're dealing with graphs of functions. One of the things that you need to understand about graphing functions in college algebra, we're doing a lot of point-by-point graphing. There are some general graphs we'll talk about, but for the most part, we're just going to plot points, trying not to make this too shortcut. We're going to just try to focus on graphing points. So for instance, the equation f of x equals square root of x plus 1. Remember, the f of x is like a y variable, equals absolute value of x plus 1. The difference here is we're focusing on making this a function. A function is a function if and only if every x value produces only or at most one y value. For instance, a circle that has one x value with two different y values would not be a function. So we're focused on things that don't have two y values for one x value. And that's why we label them f of x or g of x. What we're going to do is we're just going to pick some x's to plug in. Now, it's important to recognize when the domain stops functioning or stops working. For instance, in this problem, if I put a -1 inside the absolute or the square root here, I'm going to get imaginary values, which won't graph on my coordinate plane. So, in my x column, I'm going to start at 0 and go to the positives from there. Because if I have a negative inside of the square root, I'm going to get a domain error, and that's not good. So now the question is, what does the function do to x? And so if you put 0 in there, square root of 0 is 0, plus 1 is 1. 1, square root of 1 is 1, plus 1 is 2. 2, square root of 2, well, that's a decimal. Plus 1, well, we probably better grab our calculator at this point. And honestly, we could do a lot of this with our calculator just by going to the y equals, clearing out whatever we have, and graphing the square root of x out of the square root plus 1. And if we graph this, we get this shape. And you might say, well, what is that? Well, it's part of a parabola that's been turned on its side. But if we look at the table, there you can see those errors for all the negatives. And if we come down, okay, 2 gives us 2.4, 3 gives us 2.7. Let's just jump down to 4 gives us 3. And if we keep going, the next good number would be 9, would give us 4. Okay, so you can see this is not growing very fast. I have to move pretty far in the x to get it to work. So I'm going to go to 0 and 1, 1 and 2. And I have to go all the way to 4 to get to 3. I have to go all the way to 9 to get to 4. And so we have this parabolic shape that again is getting more and more flat as it goes to the right. And there's our graph. We might also, one of the things, so like I was talking about, one of the things we have to realize is that this graph doesn't have a domain or a range that goes forever. So if we were talking about the domain of this graph, we're thinking about this x-axis. Which values are we allowed to use? Well, it seems like here at 0 we have a value, and then if we go to 2, 1, 2, 3, 4, we can keep going this way. And there's always a graph where we live. But if you come back over here, I don't see the graph come here, because if I use negative numbers, I get errors. So for my domain, I would say that x needs to be greater than or equal to 0. Okay? If x is greater than or equal to 0, I'm going to produce a graph. If I try using something else, I'm going to get errors, and I'm going to get imaginary numbers, which I'm trying to avoid in these physical graphs. The range is in the y values. And again, if I look, from here at 1, it goes to 2, then 3, then 4. And this graph, it's going to continue to slide up ever so slowly forever, but it will go up. What seems to happen, though, is it never gets below this point at 1. It seems like the graph is always living above that. So I can say that y has to be greater than or equal to 1. Okay, and so that's how we're going to work on that. When we're looking at, we can use the graph to find information about the function. There's an example on page 216. So let's look at page 216. I know some of you don't have your book, but I'm going to grab mine real quick, open it up, and we'll take a peek at page 216. So here on page 216, we have an example with the equation we're doing example question number 2. The equation is shown in a picture. This is the difficult part about doing notes online. There's a picture, and it has several dots. It kind of looks, there's an open circle followed by, sort of has this bump to it, and then it comes back down, dips down, then comes back up, and stops there. Okay, and there's different x values and y values. But it asks us to evaluate the function at f of -1. Okay, so that'd be here at -1. We want to look and see where the function lives. What's its value? In other words, what's its y value? And if you look closely at the picture in your book, at -1, the function has a value of 2. At +1, if you come over here to +1 and you look for its evaluation, again coming all the way up here and following it over, it has a y value of 4. So we're able to evaluate the function in different ways. The domain on this is the x's, okay? And so this is actually really important. What is the furthest to the left I go? Okay, so there's this number here, which is actually -3, okay? And I can keep going all the way until this closed dot here on the graph, which happens to be at 6. Okay, so everywhere from -3 to 6 are numbers that I can plot or put into the function. 6 is included. That's how I identify the solid dot. But this first one was an open dot. Because it was an open dot, I'll use a parentheses. So this is actually the domain, and that's similar to that interval notation we were using. It's exactly the same as the interval notation we were using before. The range is a list of the lowest to the highest y value. And so really what we need to do is figure out the lowest it ever goes, which turns out to be -4. And the highest it ever goes happens to be up at +4. Just like in the other problem, +4, there's an actual point here, so that means I get to include it. But down here at -4, it's an open circle, so I use a parentheses. So we can use that graph, even though we don't know what the equation is, we can define the domain, the range, we can evaluate it. Every graph can be compared to a vertical line test. Vertical line test is a way to tell if something is a function. Okay? And so if you think about drawing vertical lines, sorry, that's not very vertical. Think about drawing vertical lines and asking the question, do I ever touch the curve more than once? The answer here is no, I don't. So this function would pass the vertical line test. That's why it's a function. Same thing with straight lines. This, however, do you see how the curve touches that vertical line more than once? It only takes 2, but this is even 3 times. And because it's more than once, we say it's not a function. So the vertical line test is a really quick test. The next thing we want to talk about is the intervals over which something is increasing or decreasing. So if you look at this graph, starting here on the left and following it, this graph is going up and up and up and up and up and up until it hits this point. So if we wanted to say that this was, where is this increasing, okay, we could say it's increasing from -infinity all the way till -3 on the x-axis. Then it picks back up, we do this union, it's also increasing, in other words, it's going up from 2 all the way out forever. So from 2 to infinity. Now we use parentheses because at 2, 2 is not necessarily increasing or decreasing, it's a flat spot. Same thing with -3, it's a flat spot. It's not increasing or decreasing. So this would be our increasing, and then for our decreasing, we would be going from -3 to 2. And if you look at this graph, from -3 on the x-axis till 2 on the x-axis, the graph itself is dropping. And that's how why we check it that way. All right, now when we talk about average rate of change, that means the slope, but what we have to realize is that as we find the slope of a curve, it's not always the slope of a line. For instance, from here to here is a straight line. But the problem is that the curve's not straight, and so its slope isn't always the same. But we can talk about its average rate of change. If you think about this as y2 minus y1, right here we have the slope equation. We're just going to do it to things that don't have straight lines. And so we'll look at it from that approach. And then we have what are called even and odd functions. Even functions are functions that have y-axis symmetry. That means you could close them like a book, and they would line up on top of itself. A function that's odd means that if I folded it across the diagonal, or if I spun it in a circle, I could get it to line back up on itself. So here, for an even function, just imagine coming right down the middle of the book, folding it. This dot would line up with this dot with this dot, and so on. It would line up perfectly on top of itself. The same can't be said for this problem. However, if I draw a dotted line at y equals x and folded it, it would line up with symmetry. One other way to do this is to spin the graph 180 degrees. If you spun it 180 degrees, this point would line up down here. And this point here would line up down here if you spun 180 degrees. And so that's a way to tell that something is odd. Hopefully that's enough to kind of support you and structure you as you go through the notes. We'll see you in class.